On today's episode, we're going to create a light sensor with these. Hey everybody, welcome to another episode of DailyIoT. Today we are going to continue on with our Internet of Things project that we started yesterday in yesterday's episode where we got our particle photon set up. Today we are going to attach a sensor to it. And it's a very, very simple sensor. It's a super cheap sensor that you can build with just two components, a photoresistor and a normal resistor. Now, a couple things for those that are not familiar with this. A photoresistor is simply a resistor that changes value. It's a variable resistor that's value changes as it's exposed to different levels of light. So in this case, as less light is exposed to the face of it here, I'm trying to zoom in on that. I don't know how you can see it. As the more light that's exposed, the lower the resistance, and the darker it gets, so the less light that's exposed, the higher the resistance gets. So that's the correlation between light and resistance on this. And what we can do with this is combine it with just a normal resistor to create what's called a voltage divider. Now, I don't want to get too much into the electronics and stuff. You can Google voltage divider. It's a very common concept when you're building projects like this. But basically, the very short version is when we hook these up in a certain way between the supply on the photon, which is 3.3 volts, or some high voltage, and ground, in the middle, we're going to get a variable voltage, an analog voltage that will change based on how the photoresistor's resistance changes in different light conditions. That was a lot of words. If you didn't follow any of that, do not worry. It'll all make sense as we continue on with the project today. But just the short version is we're going to use these two components to create a voltage divider, which is going to create a variable voltage, somewhere between ground 0 volts and our photon supply 3.3 volts. And so as the light condition changes, we're going to get some value in between there. It might be 1.2 volts or it might be 2.6 volts, somewhere in there. And we can use a pin on our particle photon to read that value and change it into a digital representation. This is accomplished using something called an analog to digital converter, which the particle photon has on board. And so it will take that random voltage in between the ground and supply value and turn that into some number between 0 and 4096. And that has to do with the resolution, however many bits of resolution that the converter has. And so, again, that was a lot of words. If you're not following it, I'm kind of fire hosing it to you right now. If this is new to you, just hang in there. You will see it's much simpler than it sounds. The technical words are there to impress people and you can impress friends at parties, but the actual implementation is super simple. You'll see what it means as we go through this here in a minute. And so that's sort of the rundown of what we're going to accomplish really quick today, and it should only take us a few minutes once we get this hooked up. Now, I'm not going to show you me connecting this stuff to the breadboard. The schematic is super simple. I will just take a picture and show it on screen here, and then we will write some code to read that value. So let's go ahead and do that now. So before we get started writing code for our sensor, I just want to show really quick how we have it wired up. It's very simple. I'll put it up right here. All we have is the photoresistor connected from 3.3 volts to pin A0. It's an analog capable pin. We're going to use it as an input. And then the resistor going from A0 to ground. And that creates our voltage divider across A0 so that the voltage will vary right on that pin as the light conditions change. So that's how we're going to wire it up. And now we're going to come back into the particle IDE here where we were yesterday. We had this blink LED sketch up, and we're going to create a brand new one. So I'm going to come over here to create new app, and you can see it wants me to give it a title. I'm going to give it just light sensor and hit enter. And now it creates this shell of code. It says void setup and void loop. These are the two functions, like we talked a little bit about yesterday, that are going to be in every sketch for our particle photon. The setup function is going to be run once, and that's the first thing that will happen. We're going to take care of any initialization that we need to do there. And then the loop function will be executed over and over again. As soon as the loop as soon as the loop function finishes, it will immediately execute again. And that's sort of the flow of code on our particle photon. So in the case of our sensor here, this is going to be very simple. We're going to come in here and we're going to say pin mode, and we're going to choose our pin, which is A0. We can address it exactly as it is listed on our photon, and we're going to give it a mode. In this case, we want it to be an input. And what that does is configures the pin to be a GPIO input pin, ready to read voltages. Now at this point, it can be either a digital input or an analog input, and that distinction is only made when we actually go to read the pin, which you'll see in a second. Now the second thing I want to set up is my serial port. So I'm going to say serial.begin, and I'm going to give it a baud rate. I'm just going to say 9600, and this is just saying serial is a variable that we can use to address the connection that we have to through our USB port on our connected PC, in my case my laptop. And saying begin means go ahead and get that all set up and configured to operate at 9600 baud rate. And that's it. That's all we have for our setup. And then down here in our loop, all we're going to do is read a value. So I'm going to come up to above my setup, and I'm going to initialize a variable up here of light value. And then in our loop, I'm going to say light value equals analog read, and then the pin that I want to read, in our case A0, if I can type it right. There we go, A0. So what that's going to do is say A0, that's configured as an input, give me the value of the voltage that you're sensing as an integer. And again, that's going to vary between 0 and 4096, and those numbers just happen to be the fact that the analog to digital converter is a 10-bit analog to digital converter. Actually, sorry, I mean that's a 12-bit analog to digital converter. And a way that we can look at that actually is if we just launch our calculator app here and we do a 2 to the 12th power, you'll see 4096 is the max value there. And so in a case where a platform may tell you that the analog to digital converter is 10-bit or 8-bit, but they don't explicitly tell you what the number range could be of an integer, you can figure it out really quick. You just do 2 to the power of whatever bits of resolution it provides, and it'll give you the range. In our case, 0 to 4096. And so, okay, back in our code here. So light value is going to have some value after we do this analog read between 0 and 4096. And then all I want to do is print it out. I'm going to do serial.println light value. And what that's going to do is basically put that value out across our serial port so that we can read it on the other end, and I will show you how we will do that. And so that is all the code that we need. Oh, one more thing. So if we leave it like this and we build it, what's going to happen is it's going to do an analog read, it's going to write it out over the serial port, and then it's going to do another analog read milliseconds later. This thing's going to be reading and trying to print out so many readings so quickly. And so what we want to do is we're going to put a short delay in here by just using the delay function. We'll say 1000 milliseconds, which is 1 second. And so it will print out the value, it will delay for a second, and then it will repeat the loop again, get another reading, print it out, wait a second, over and over and over. Okay, so let's go ahead and see if we've done everything correctly. We can click this verify button. It'll say compiling code down here at the bottom. It says code verified, great work, excellent. And then as long as our photon is plugged in, which mine was not, let me plug it in there really quick, and it's connected to the cloud, we can click this flash button, and that will go through the process of taking this code, updating it over the air onto our particle photon, and begin executing it immediately. And now that that code is running, a perfectly good question is, how do we see the output? And it's actually very simple. We're going to come back over to our command or terminal window that we were using yesterday to install the particle CLI, and we can just use that same particle command line. We'll say particle serial monitor. Now there's other options that you can pass to this, like which serial port you want to monitor and things like that, but it does its best to figure out what the default is and looks at your attached devices and looks at things like the manufacturer to try and just find which of the things that are connected to this laptop is probably a Photon. Let me just connect to that. And so it does a really good job. I'm going to hit enter, and you'll see opening serial port, serial monitor for COM port, and that's the path to my Particle Photon that's connected. And you can see that I'm getting readings coming out there. And so I'm gonna keep this up on the side here, and if you see I've got this over here, if I hold my hand over it, you'll see that the reading goes down. I'm down to 160 and 70 and things like that. Then if I grab my phone right here and get the flashlight up and hold that over there, you'll see the value goes way up. And if I hold it right over, I think I can get it pretty close to 4,000. Shine that right on there. But anyway, you can see how our value gets higher when more light shines on it and gets lower when less light shines on it, or if we kind of shade it, make it go down. So, okay, and that is it. That's all it takes, just a few minutes. And we have a light sensor hooked up to our Particle Photon that we are getting readings from. Now, a couple things to note and remember. A lot of times in electronics, you can hook things up backwards. Sometimes capacitors and power supplies and things, LEDs, you need to make sure you're hooking up a correct way. A photoresistor is not one of those components. You can hook this up either way on your breadboard. It doesn't matter. You're not going to hook it up backwards and ruin it or anything like that. Another question people have is, in our case, we connected the photoresistor from 3.3 volts to our A0 pin, and then our normal resistor from our A0 pin to ground. Now, what happens if we switch those? What happens if we had the photoresistor on the ground side and the normal resistor on the positive side? That's a good question, and I would challenge you to explore that. Go ahead and try that. Give that a try and see what changes. I just want to, preempt that with, you're not going to break anything. You can go ahead and switch those, but it's interesting to see. And then if you can combine that with stuff that you're reading about voltage dividers, I think there's a good bit of learning there about how this stuff works and just general electronics knowledge. So I'm not going to give you the answer on that one. I would encourage you to play around with it. Now, if you don't have the components to play around with this at home, you can fast forward to the end of the video and I'll give you the spoiler alert information on what happens. But anyway, that's all it takes. That brings us to today's word of the day, which is analog. Now, we've talked about GPIO pins, general purpose input output, and we talked about how those can be inputs and take voltages in and read them, and they can output voltages high and low. We talk about two different kinds of output and input, digital and analog. And our light sensor is an example of an analog input. And again, all that means, analog, all that means is that the value can range to any infinite number of values in between two end values. In our case, 0 volts, which is ground, and 3.3 volts, which is our positive supply on our Particle Photon. And so because it's analog, it can be any voltage in between there. There's an infinite number of voltages it could be in between those two values. Whereas digital would be, it's either 0 volts or 3.3 volts. And so that's our word of the day, help you understand a little better how analog works and how it's a little different than digital, but how it can be used in a simple circuit like this to provide us valuable information about the world around us. And we can then interpret that information and do something with it, which is how we will pick our project up tomorrow. Now that we have figured out how to connect this simple sensor to our Particle Photon and communicate with it in our code, our very simple code that we wrote, we're ready to take this to the next step, which we will do tomorrow to see how we can now get this information off of our local photon and laptop and into the cloud and really make this the Internet of Things and not just the things. So hope you can tune in tomorrow to see how we do that. Hope you're catching on and kind of learning some of this as we go. If you have any questions, please put them in the comments down below. I am happy to help and answer those. Otherwise, thanks for watching Daily IoT, the show where together we're learning all about the Internet of Things, one day at a time. Okay, during the episode, if you've watched it this far, I said at the very end I would give you the spoiler alert of what happens if you switch the resistor and photoresistor in our schematic. I wanted to make sure that people that don't have access to this can still get the information of what will happen. And so when we hooked this up, we had the photoresistor going from 3.3 volts to A0 on our photon, and the resistor going from A0 to ground. And what that did was when the photoresistor got a brighter light, our value in our code went up, it increased. And as it got darker, the value in our code decreased. And that seems very intuitive. It seems like, oh, as it gets darker, the value should go down, and as it gets lighter, the value should go up. However, if you switch them, put the resistor from 3.3 volts to A0 and the photoresistor from A0 to ground, all that will happen, nothing bad will happen. Remember, these are just two resistors, you're not going to hurt anything, is that the opposite effect will occur. And so as it gets darker, the value will go up in our code. And as it gets brighter, the value will go down. And there may be a scenario where that makes sense. In your code, it may make sense to flow of like, I want to know, I can't think of an example off the top of my head, but it may make sense that that would be the behavior. And so really it's just a matter of how you want, you can actually control. This is sort of like combining programming concepts with hardware, which is, it's more intuitive in our case for the number to get higher as the light gets brighter. And so we wired it up that way. However, like I said, you may find a scenario where the opposite would be more useful for you. And you can always translate the value in code. So anyway, that's what happens if you switch them. Nothing bad, just you get a different behavior. The voltage will change. Again, you can read up on voltage dividers on Wikipedia. I put the link down in the description below. So now you know.